Chapter 12 continues the examination of propositional logic with the analysis of argument form. We'll be looking at techniques for determining the validity of propositional arguments. You'll remember that any valid argument is one whose premises, if they are true, ensure the truth of the conclusion. In other words, if the premises are true, it's impossible for the conclusion to be false. Only deductive arguments can be valid. We can determine validity with truth tables or with standard argument forms. We can also use these forms to identify some notorious formal fallacies, specifically affirming the consequent, denying the antecedent, and affirming a disjunct. We'll consider proof construction and the famous reductio ad absurdum in a separate unit. Let's start with truth tables. You'll remember that truth tables can be used to identify tautologies, that is, compound statements that are true under all possible circumstances, contradictions, that is, compound statements that are false under all possible circumstances, and contingencies, compound statements whose truth or falsity depends upon the value of their simple components. What makes truth tables so useful is that they enable us to see whether an argument is valid with 100% accuracy every time. They're like little machines that yield perfect results, if we know how to use them correctly. Let's examine this argument. First premise, either buffalo are prairie animals or coyotes are. You'll recognize this as a compound statement which is disjunctive. The second premise, buffalo are prairie animals, is a simple statement which affirms one of the disjuncts introduced in the first premise. Conclusion, so coyotes are not prairie animals. Let's lay bare the formal structure of this argument. First premise, B wedge C, which we can also read as B or C. Second premise, B. Conclusion, therefore tilde C, which we can read as therefore not C. Now we're going to put the lines in this argument into a single horizontal row. Separate the premises with commas and insert the symbol for therefore just after the last premise and before the conclusion. The result will look like this. B or C, comma, B, therefore not C. Now we'll build our truth table. We'll start by drawing two intersecting lines. At the top right, we'll enter our argument's formula, the two premises together with the conclusion, and at the top left, we'll input each simple proposition that is used in the argument. It'll look like this. As you can see, we've now supplied our truth table with its header row. We're now ready to assign truth values to each of the argument's simple propositions. How many different combinations are possible? In a binary logical system such as this, there are only two. A statement must be either true or false, so we'll always use 2 as our base, since there are only 2 values in this system. Next, we'll determine how many rows the truth table must have by raising base 2 to the second power, since we only have 2 simple statements to account for. 2 to the second power is 4, so we'll have 4 rows in the truth table. It will look like this. As you can see, the header row has 2 parts. The argument itself is on the right, and the simple propositions it contains is on the left. Underneath each simple proposition, we have arrayed all the possible combinations of truth and falsity the 2 simple propositions can have. There is the case where both B and C are true, the case where B is true and C is false, the case where B is false and C is true, and the last case, in which both are false. You should always use this same pattern in truth tables that have only 4 rows.